What's up, guys? Welcome to another video brought to you by The Simple Engineer. Today we are going to break down IPv4's CIDR, and we'll talk a little bit about VPCs, and also we'll talk about natting and some introduction for a little bit of history to all of this stuff to make it a little bit more interesting. So without further ado, let's just dive right. First thing I want to talk about is an IP address. What exactly is an IPv4 address? What's the composition of it? We should all probably know that, IP addresses within a network, this is how, devices communicate on a network. So if I have a computer on my home network and I want to print something, well, it sends it over to the IP address of my printer, and that's how they communicate. Very much like humans go to each other's houses, or they go to a venue, they locate it by its address, and that's kind of how we navigate through, and that's exactly how it's done on a computer network as well. So what we're looking here at the top is the decimal form of a IP address, and this probably looks very familiar to you because this is typically how we see them. And below is its binary counterpart. So IP addresses, at least for IPv4 specifically, it's important to note that these values are 32-bit values. So what we see here is we have a single octet, which is consisting of 8 bits, and we have 4 of these, and this is what comprises an entire IP address. So if we do some very simple elementary math, we can take 2 to the power of 32, and that tells us that for IPv4, there are a total of 4.294 billion possible IP addresses within this space. So before we go too deep, just going to quickly touch on the idea of classful networking. So in classful networking, we essentially have 3 classes, A, B, and C. And we'll see that the first 8 bits here are used up, and the remaining 24 are left for the host ID. And this is what's known as a /8 block. Now, if you don't know what that means, we'll dive into it in much more detail in the coming slides. But we have 24 bits, which basically says that we are leaving 24 bits of available IP addresses. In other words, what this means is 2 to the 24, which is 16.7 million IP addresses within this range. When we have a 16 bits for the host ID, that's 2 to the 16, which is roughly 65,536, I believe. And Class C is going to be 2 to the 8, which is 256. So when companies and corporations, they, try and get some block range or some block space, they essentially try and fit how many IPs that they need. So in a Class A system for 24 bits, that would be a lot of IP addresses. That would be 16.7 million. Class B is going to be a little bit different because this is going to be 65,000, so this may be for a large corporation. And then Class C might be for a smaller business. But in any case, if we need 2,000 IP addresses, this is kind of a problem because we would have either we'd be doing a Class B, which would be wasting potentially, over 60,000 IP addresses, or Class C, which just doesn't have enough IP addresses, and maybe we would need to create a bunch of subnets and complicate our routing table. So although it did help from stop over allocating unused IPs within our blocks, we still have this issue where we're basically throwing away unused IPs and we're being extremely wasteful, and this in turn was diluting the available IPv4 address space much quicker than needed. So you may be wondering, well, we have 2 to the 32 IPs and there are billions of people in the world. We must be running out of IPv4 addresses. And the answer to this question is yes and no. So it's yes because, there are a lot of people on the internet. So we have 2 to the 32 possibilities, but the population is large and IoT is taking over. So all sorts of things are connecting to the internet. We have toasters that are connected to the internet. We have refrigerators. We have your cars, cell phones, etc. These are all taking up IPv4s, and of course, it is shrinking the available number of addresses. So, is there a solution to this? Well, IPv6 is the next solution, but not so fast, right? Although IPv6 is kind of this great solution, we have 3.4 times 10 to the 38 possible available IP addresses, it doesn't necessarily solve the entire problem. And the reason being for this is because, for everybody to just stop using IPv4 and migrate over to IPv6 is a very challenging problem. And the reason this becomes so challenging is because, a lot of software and hardware was designed around the IPv4 protocol. So for, software and hardware to interoperate with one another, to communicate to different servers, to, transfer data over the network, everybody's was really using IPv4. So to just switch everything overnight to IPv6 becomes a very, very complicated problem, and it's just not possible to do overnight. Just to give you an eye into IPv6, it was actually introduced in 1998, as this problem has been thought about very carefully, and we're still not fully migrated to it in 2018, and it's just a very large migration process. So what you're looking at here to the right is a map, an XKCD comic, which basically shows people that have purchased /8 blocks, or basically they own 16.7 million blocks of IP addresses within the public IPv4 address space. This is kind of interesting. We can see that Boeing has a block here for a /8 block. We have people like IBM. We have the Department of Defense, which actually owns several IPv4 blocks, /8 blocks, and then a bunch of registrars. So back in the 90s, there was this 90s problem, and the 1990s /8 problem was basically a bunch of these large companies came in, or government organizations, and they just bought up blocks of IPs before registrars were really the authority here in the space. And as a result, there are a lot of blocks that were just straight up used that may be being wasted today. And to give you some insight, a /8 block today is worth about $200 million to $1.5 billion. So very, very expensive. And this is just an interesting table I found on the web that shows companies, how many blocks they own, and how many IP addresses are associated with it. So the Department of Defense has 12 blocks of /8 blocks in the IPv4 address space, which is 201 million IP addresses. And you can see that just this small chunk here takes up a very large percentage of the overall available IP addresses. So that's kind of why we have this problem of shrinking number of IPv4 addresses. So we have a solution to this diluted number of IPv4 addresses that we're running out of. NAT and CIDR save the day. Or do they? So NAT and CIDR saves the day because they enable packet rerouting to private IPs. And we'll understand what that means on the next slide, but it's going to slow down the IPv4 exhaustion problem. But at the end of the day, this is kind of an awkward band-aid to the problem because we still have 2 to the 32 available IP addresses. That number's not going to change. But this is kind of a small resolution, at least in the short term or maybe even long term, for allowing us to reduce the number of IPv4s that we're taking up. So what exactly is NAT, or what exactly is network address translation? Well, this is really the simplest slide that I could put together to demonstrate this idea. Typically, in your home network, you have a router, and the router is going to be assigned an IPv4 address. And this is going to be one of the, within the 2 to the 32 address space, this IP is going to fall within that range. But in addition to that, in your router, you have a bunch of devices that are connected to it. So you have your laptop, you have your toaster, you have your internet connected toothbrush, what have you. And all of these things lie behind your router or your network. And each of these devices are assigned a private IP. So what happens is the private IPs are actually not taking an IPv4 address. This is within a CIDR block, and we'll look at that as well. But what this is saying is we can essentially have n number of connected devices that are all connected to the internet, but they're all proxied through a NAT gateway on our router. So really we're only using up one single IP address that's supporting potentially tens, if not hundreds, of devices within our network, and it's all being connected to the internet. So how does this work? Well, what happens is, I'm on my home desktop computer and I go and I make a request to view the front page of Yahoo News. So what happens is I create a request from my computer and it goes through my router. Now, what the router does is it kind of intercepts this packet and it wraps it with some metadata with this IP address, and it goes and it sends it out to the network. It goes and sends it to Yahoo server, and Yahoo server does some computation and sends back a response. So the problem is the response is going back to the router, but we need it to go back to the host that actually made the request. This internet out here, Yahoo, it doesn't know how to give a ping back to my actual desktop computer. That's not where it goes because this is a private IP address. What it does is it proxies through the router and it looks at the network address translation table. It looks at the routing table and it says, oh, I'm going to take this packet and I'm going to route it back from the router to the desktop, and the desktop is going to get the response and everybody's happy. So for a device in your home network to get internet access, it doesn't go directly to the internet. That's not what happens. It goes through the router, and the router, has this NAT gateway that basically allows open access to the internet, and then responses get sent through here, and then proxied through this routing table to send it to the correct place. And that's basically the idea of NAT. So this is really nice because this allows us to reduce the number of IPv4s that are getting exhausted within the address space. So this brings us to the fun part of the lecture, which is CIDR. And CIDR is classless interdomain routing. So if you remember before, I was talking about class IP ranges, which were basically class A, B, and C. And this was the problem where, I can have either 65,000 IP addresses or I can have 256, but I can't have anything in between. So what happens is I end up wasting a lot of IP addresses. Well, CIDR is the solution to this. It reduces IPv4 exhaustion, which is a big thing, and it also simplifies routing tables, which is kind of like what we were looking at with NAT, where it routes things easily to these private IP addresses. So private IP addresses, their available space or their private IP ranges were specified and declared by the IANA, which is the Internet Assigned Numbers Authority. So what you'll commonly see is starting ranges can either be 10.0.0.0 or we have 172.16.0.0 and 192.168.0.0, and these are the ending ranges for these spaces. So in order to understand the CIDR notation, which it does have its own notation, is we have an address here, which is going to be the network prefix, and it's followed by a slash, which says what the network prefix length is. So we have the address and the network prefix length, and then any remaining bits are left for the host ID. And the number of bits in the host ID basically specify the number of IP addresses that you can have within your CIDR block. So what I want to do is I kind of want to switch over and do a little bit of math and talk about this in more detail. So on Amazon AWS, you can create a virtual private cloud, which is basically your own virtual network. And that's exactly what we're going to do to kind of demonstrate this idea in more detail. So I'm over here in the AWS Management Console, and I'm just going to click on VPC. So if we just go ahead and create a VPC, and even if you don't know AWS, this is just very big. Call this demo U2 VPC again. And the CIDR block, again, will be 10.0.0/20, which is 4,096 IPs. And now we want to create a subnet. So what exactly does this look like? Well, what we have is we have the network that we've created, and this has 4,096 total possible IP addresses. And what we want to do is we want to create a public or private subnet, and we want to take a subset of these IP addresses and allow them to be assignable within just this little subnetwork. And then maybe we'll have another private subnet that takes another subset of this 4,096 in its own subnetwork. And we can divide this in as many subnetworks as we want, and they're all going to be subtracting from this total of 4,096 that we specified in our VPC CIDR. So we're going to go ahead and create a new subnet for our VPC. I'm going to call this, public subnet 1 or a IPv4 CIDR block. So we need to compute something that's going to be valid within our range. Well, keep in mind, this is our VPC CIDR. So you may be asking, okay, so with a CIDR of 10.0.0.0/20, how do I calculate my range? Well, we know the starting range is going to be here. So this is definitely the starting range. But what's the ending range? Well, the ending range is going to be basically whatever the negated decimal form of the network prefix value is. So what does that mean? Well, in a 32-bit value, this 20 says the first 20 bits are going to be turned on. So if we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Then the remaining 4 of this octet are zeros, and then the final 8 are zeros. So this is what this 20 is essentially specifying. So we need to convert this into the ending range. And the way that we do that is we take all the ones, we turn them into zeros, and we take all the zeros and we turn them into ones. And then we convert it into its decimal form. So all of these, when they're zeros, just 0.0. And then we look at this, and if this becomes 0, 0, 0, 0, 1, 1, 1, 1, we turn this into a decimal form. Well, we know that this in binary is just 15. So what I can do is I do 15 here, and then all ones, when we negate all of these, they turn into all ones, which is 255. So now we have 0.0.15.255, and we basically mask it over what the starting range is, which creates an ending range of 10.0.15.255. And this is our ending range. So now we need to pick a valid IPv4 CIDR block for our subnet here. How do we do that? Well, in order to calculate this value, in order to be able to do this, we essentially need to just come in here and say, okay, well, I need to first figure out how many IP addresses that I want to even assign in my public subnet. We have 4,096 total, so I can't assign any more than 4,096 because that would exceed the number of assignable IPs in general. So if I came in here and I said something like, 10.0.0.0/19, we would just get an error, right? Because it exceeds the number of available IPs. We could just off the bat do all of them, and this public subnet would just use up all 4,096, and then any other subnet would not be able to have any IPs assigned. But we don't want to do that. We just want to do a subsection. So, for example, let's say that I only want 16 IPs, then I could, well, I think actually Amazon has a minimum, and they may tell you So /28 is the smallest net mask that you can do on AWS. So if we did something, a /28, what that means is we have 32 minus 28, which is 4. So 2 to the 4 is 16 available IP addresses. So that's what I want. That's the number of IPs that I want in my public subnet range. So then I need to figure out, okay, well, what's a valid network address for that? So it's going to be 10.0.0.0/28. This would be valid. But what if I wanted to change it? What's another valid one? Well, the 28 essentially means that the last 4 bits of my IP address need to be reserved as zeros. That's all that means, the last 4. The rest can be whatever they want. So, for example, I could do 10.0.1.0/28, and this would be valid as well. And I can go all the way up. See, we have our ranges here, so I can go all the way up to 15. So I can make this 10.0.14.0/28. And we can even try this. I can go back into my CIDR block, and I can change this value to 14. And this would have to be 28 now. And you see we don't get an error message. And I could change this to 15, and it would work. But the second I go to 16, we exceed our available ending range, and we would get an error. See? So that's why that value isn't valid. But then, what can I put here? Well, keep in mind that this value can range from our calculation all the way up to 255. But what happens is these need to be offset by the number of IPs that we are utilizing. So for example, since we're doing /28, that means we have 16 IP addresses. So this ending number basically has to be a factor of 16. So I can do, if I did a 15 here, it would error out, but I could do a 16 here because it's an even offset. I could also do something like 32, for example, and I can do something like, 96. But keep in mind, we need to be within that 255 range. So if I did something like 255, it's going to fail because it's not evenly divisible by 16. But 255 minus 16 is 239. So this could be 240, because actually 256. So 240 is valid as well. And we know 240 divided by 16 is 15. It's evenly divisible. So this is a valid CIDR block. And then these numbers can just be toggled between 0 and 15 as well. So this could be 13, 11, etc. These are all valid numbers. And that's pretty much how you do the calculation for the IPv4. Pretty much it. That's kind of CIDR in detail, how the calculations and formulas all work together, and a little bit of history about IPv4. If you guys have any questions or comments in the video, please feel free to shoot me a message or leave a comment below. And that pretty much does it. So thanks a lot. See you in the next video.